Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Mukriz Memazan. I'm a semester 6 student, candidate for masters, and this is my progress report. I am based in FTTC. I am under Professor Madiati S. Dr. Reza Effendi of the College of Engineering Mechanical Engineering. My thesis title is Flight Simulation Assessment of Novel Fixed-Wing Multi-Rotor Hybrid Agriculture Drone. This has been a long-standing research and has been carried out for the past 2 years. Within these slides, I will be going through all of these contents as stated in the slide. The introduction to my project is that the agriculture industry in Malaysia has seen quite a bit of use of multi-rotor drones as to promote more agriculture as well as cultivate the large vast amount of land that has been used in agriculture. These drones are typically used to spray insecticide as well as surveying new possible fields for new growth. Typically in Malaysia, they use a multi-rotor configuration, which is arguably one of the most stable ones, but lacks within the confines of efficiency as well as the skills for the common farmer to learn to operate them. These drones, of course, are always used to replace the traditional way of cultivating land using the four-wheeled vehicles, and sometimes these things can be very dangerous as well as very tiring for the workers. So these drones are the main source of working machinery for the new age of agriculture. My research is to provide another form of this, albeit a much more efficient, energy efficient, as well as much more stable for farmers to use. The novel design, the fixed-wing multi-rotor hybrid, is a culmination of Dr. Reza Effendi's ideas on a VTOL-capable fixed-wing aircraft. This, of course, is a new field of aviation, as only some examples are seen in real life. The main takeaway on why this design is novel is because it does not have any control surfaces on its wings. It mainly uses the four multi-rotors to conduct its drag, pitch, yaw, and roll. It is estimated to be able to carry 5 kilograms of insecticide for a full-scale 10 feet long wingspan. With context, the project aims to have an easy-to-fly UAV for farmers. It reduces the cost of purchasing as well as reducing the cost of manufacturing it, and of course to improve on the agriculture industry and to help farmers in Malaysia. My objectives are as follows. I am here to investigate the flying quality and the dynamic stability of that fixed-wing multi-rotor hybrid, to synthesize a suitable control method augmentation, and to evaluate the flying quality of the control method augmentation. This, of course, was presented on my last videos. Now, for the progression of this semester, I'm here to show happily the progress that I've made this semester. So again, this is the design. As you can see, it is a fixed wing aircraft that has 4 props that is used to carry it into the air as well as to control it in the air. The design, after which I've been used Flight Simulator to design it, we transfer it into the AutoCAD software, and then furthermore going into a 3D printing software. This process took a lot of time to figure out, but albeit it is a very insightful process, as well as a learning curve that I believe is one of the novelties of my research. As you can see from the video on the right, I've printed the first batch of the design into using the PLA of the 3D printing process. This of course is quite difficult, as the amount of work that is required for this is quite arduous. The first designs of the aircraft, once I 3D printed it, is quite fragile, albeit because of the design we took it from the flight simulator software and then turned it into a wire mesh into the CAD software. But once we ironed out some of the materials, it made the structure much more strong. As you can see from the pictures, this is my effort to strengthen the structure. After 3D printing, of course, we would coat it with a thin layer of epoxy to make it more sturdy, as well as having it able to withstand forces during flight. This is the prototype that was mentioned in my previous video that I will be using to compare the flight simulation data. As you can see, the progress we've made this semester is mainly on the electronic side. I have connected the Pixahawk fully integrated into the fixed-wing multi-rotor aircraft. This of course requires the usage of several components. Mentioned the flight controller, the motors of course, the radio controller, the radio receiver, and ESCs. As you can see from the SLD of the diagram, you can see that the Pixahawk is connected to a ESC, of which it will control the speed and rotation of the 4 rotors. Us as the controller, holding the radio controller, we decide where each of the motors, each of the motors do corresponding to the sticks. From the video, you can see that this is my first attempt of connecting to the motor. This is the first attempt because I am just connecting the power source, which is just a LiPo battery, to an ESC, and then connecting to a motor, as well as having the radio controller connected to the ESC for my commands to be given to the motor. There is no complexity for this. It's a simple one-way exchange. It's me giving a command and then throttling up and throttling down. The second video is combining all four of the motors into one controller connected to one flight controller, and this is me testing the capabilities of it. This was fairly hard because as some of you may know, the power source distribution is quite difficult for for any multi-rotor, but I've worked around it using a PCB board that's custom made for the Pixahawk to give power to the ESCs and the motors. This is completely integrated with the flight controller, and this really helped the process of controlling the aircraft. I used simple soldering methods to solder the wires to the ESCs and soldered the power source wire to the power source points. Yep. And the last video is the assembly and the integration to the fixed-wing multi-rotor aircraft. This is just me showing that all of the motors are connected to the motor mount, and the objective now is to clearly just try to test fly it.
Okay, Prof.
Going forward, the next achievement I believe is the acceptance of my paper. This is one of the first. This is one of the research papers that I have submitted for this research. This was given in the International Conference of Smart Technologies, and I will be getting the details soon with the uh, code for the research that I'll be putting it into my thesis. This is a few pictures that I wanted to show of the progress, mainly the wiring and the upkeeping of the design, putting everything into the fuselage as you will, and to make it more compact and much neater. It's a very difficult task because this is also need to also remember that any aircraft, any weight load best to be put at the CG, the center of gravity, which is at the half point, sorry, 1/3 point of the start of the wing, at the center of the fuselage, of course. That can prove a bit difficult, but I've worked around it, and hopefully it can uh, be much more stable that way. In my Gantt chart, the progression from last semester was the implementation of that the aircraft into the real world, making it into a proper prototype, and now is the point of comparing it with the theoretical data and the flight simulation data. In the thesis that will be presented for this research, it will cater towards the comparison between the likelihood of that aircraft behaving in the flight simulation, as well as the likelihood and behavior of the aircraft in real life. With that, that will be my final research point for this aircraft. So my plans for the next semester is to fly the prototype and the publication of the research to other journals, as well as submitting my letter of intent to the Senate. Thank you.